Okay, so chapter 23. So alcohols, naming, remember when we come across a new functional group, it's going to be naming, physical properties, and then chemical properties. And the chemical properties are all given consecutive numbers of the type of reactions. So the root is the longest continuous chain that includes the alcohol group. We leave out the final E, make it end in OL. Then we give the hydroxy group the lowest possible number. And then we put the substituents in alphabetical order. So here's the alcohol group. So now we're going to name this as an alcohol. So the longest continuous chain that has to include the alcohol would be 5, right? So pentanol. So if this were the pentanol I chose, then it would be at carbon 1, 2, 3 or 1, 2, 3. So it doesn't matter which way I go, I'm going to get 3 pentanol. And then you got 2 methyl groups. You're on 1, 2, and 4, right? So 2,4 dimethyl 3 pentanol. An alternative naming system would say 2,4 dimethyl pent, and they put the 3 in front of the all. So here's another one. The longest continuous chain has to include the alcohol. So 1, 2, 3, 4, or 1, 2, 3, 4, 5. So it's going to be pentanol. This would be carbon number 1. So 1 pentanol. And then this would be the alkyl group, right? Which would be 2 ethyl. And then common names give the alkyl group and then the name of the functional group, which is in this case alcohol. So methanol, and notice I don't have to put the 1 in front of it because we don't need it. It's also known as methyl, methyl, and then it's an alcohol. Similarly, ethyl, and then it's an alcohol. So here is 1 propanol, but it would be propyl, then alcohol. But more precisely, they probably would put N-propyl to tell you that this is different than isopropyl. And this would be 2-propanol, but this would also be the isopropyl group. So isopropyl and then alcohol. And here's the tert-butyl group. So tert-butyl, tert-butyl and then the alcohol. But if you look at the longest continuous chain, it's only 3, no matter which way you go. So it's propanol on carbon number 2, and also on carbon number 2 is a methyl. And getting into slightly more complex names. So sometimes the names are derived from the pieces that make up the molecule. So this right here would be propanol. So this would be carbon number 1, so 1 propanol. And even though this is smaller than the cyclohexyl group, the cyclohexyl group is treated as a substituent. It's just easier to name that way. Otherwise, you'd have to have a name for this, a name for this, a name for this. So here would be 3 cyclohexyl, 1 propanol. Here's 1 cyclohexyl, 1 propanol. Here's cyclohexyl methanol. So notice this name is methanol. So they're treating the cyclohexyl ring as a substituent. So same thing here. This would be ethanol. And then on the carbon number 1, there's a cyclohexyl group. But in addition to the cyclohexane, it has a methyl group on here. So it'd be called methyl cyclohexyl. And here's a case where we have to put the whole thing in the parentheses to make it logical. So this whole thing is on carbon number 1. But if you make that the priority of this carbon 1, that's 2, that's 3. So that's 3 methyl, 1 cyclohexyl ethanol. And so here's a similar one, right? And then this, you're going to have to remember, is phenol. So I usually say phenol. Some people say phenol. But you need to know that now. And then here's propanol, right? So 2-phenyl is on the 2-phenyl group. And then this one, this is the benzylic position. Okay, so we talked before about this being ortho and para, ortho and meta and para. But this one right here is called benzyl. So we could call it phenyl methanol, but this is a common name is benzyl alcohol because the alcohol group is up to benzyl carbon. And then naming diols and triols is similar to alcohols, except you use the word diol or triol. So here is 3 in a row, so it's propane and it's a diol. So we have to say, well, where are the 2 alcohol groups? It would be carbons number 1 and 2. So these are what's called vicinal alcohol groups. They're right next to each other. That term is vicinal. Here's another one. Here's butane, and it's a triol. So you have to say where the alcohol groups are, 1, 2, and then finally 4. This is also called a glycol. A glycol is any molecule that has vicinal alcohol groups. So this is also a glycol. And then we have ethane, and it's a diol, and it's 1, 2. And the common name for this is the ethylene group, and it's a glycol. So ethylene glycol is what they put into radiator fluid. Okay, so that's used in antifreeze. Here's another one that's really important. So 3 in a row, so it's propane, it's a triol, and it's 1, 2, 3. Propane triol, the common name for this is glycerol. So glycerol can be treated with nitric acid to produce trinitroglycerol or nitroglycerin, okay, which is what's in dynamite. So could I do this in the lab here? Yeah, I got lots of glycerol. I do have some nitric acid, although I am watching the chemical safety guidelines. They're getting more and more strict about who has nitric acid. But anyway, nitroglycerin is extremely dangerous because it's shock sensitive. And so if you are trying to make it at home and you drop it on the floor, that could be the end of the floor and possibly you. So it was Alfred Nobel that found a way to stabilize nitroglycerin. He used diatomaceous earth, which is like a clay. And anyway, he made so much money off of making dynamite that he's the one who started the Nobel Prize. Well, he started after he was dead, so it was even more amazing that he did that. So methanol is called wood alcohol. It's made by bacterial fermentation. It's actually quite dangerous because it gets oxidized into formaldehyde, cause people to go blind and will kill them. Actually, hundreds of people a year die from methanol poisoning. So ethanol, of course, is the inebriating alcohol. You guys are college students. You're experts on that already, right? So what about the physical properties of alcohols, diols, and triols? Well, The carbon-oxygen bond is polar. The oxygen to hydrogen bond is very polar. And so yes, they can do hydrogen bonds. I'll have to draw that on the iPad over here, try to do that. So alcohols can form up to 3 hydrogen bonds between themselves, 3 hydrogen bonds with water. So that means that they have pretty strong attractive forces. And so just to give you an idea of their solubility, methanol, ethanol, propanol are miscible. That means you cannot get a saturated point. So here you see the boiling points go up simply because of the mass effect, right? They're getting sequentially bigger. Then you get to butanol, which, by the way, butanol stinks. It's a really foul-smelling alcohol. It's soluble, but only about 8% so. Okay, become 8% solution, it's saturated. Too many carbons, then you get one more carbon and it's only slightly soluble. Other ones I can't get real values for, but then you get to octanol, and it's basically insoluble. So what about now? I made a diol. So I took this blue one right here with only one alcohol and I simply added another alcohol, and what do I get? It now becomes miscible. Okay. Even if I take this one with 9 carbons in a row, nonanol, if I put another alcohol in it, it at least starts to become soluble. So you can see the effects of more than one alcohol. So I'm going to, let's see, how does this work? So I'm going to show you how to draw hydrogen bonds between alcohols, and I'll just use methanol. So here is methanol. Okay. So if I look at the difference in electronegativity, it's a polar bond, especially this one over here. So this would be the partial positive. This would be the partial negative. And notice that I also have a partial negative down there. So now if I have a partial negative, that's going to attract the partial positive of another molecule. Well, if the molecule is just like this, where is the partial positive? It's on the hydrogen. Okay, so what kind of interaction is this? Does it have London's attractions? Yes. If they collide with one another, they have London's attractions, but that's weak. Is it a dipole to dipole? Here's a dipole, here's a dipole. Does it meet the criteria for being a hydrogen bond? Here's the OH in one. What does the other one have to have? An F, an O, or an H, and then here's our O. So that's one hydrogen bond. Here's the partial positive that would attract the partial negative of another water molecule, of methanol molecule. So that would be the electron cloud on the oxygen. So if I draw the rest of the molecule, there's an attractive force. Here's the OH of one. What do I need in the other one? An F, an O, or an H, and there's the O. So that's 2 hydrogen bonds. I didn't give myself a lot of room right here, but this partial negative would attract the partial positive. That would be on a hydrogen. So now I see that I had 3 places with partial charges on there, and all 3 of those places could potentially be a hydrogen bonding place. So in methanol at room temperature, do I really have 3 hydrogen bonds? No, it's probably more like an average of 1 or 1.5. But when you draw the maximum number, it gives you an idea of how strong those attractive forces might be. Now, what if I was going to draw this with water? What would I do? What would be different? I don't know if this will show up or not. Let's see. All I would be doing is changing this methyl group to a hydrogen. See that? So one methanol molecule could form a maximum attractions of 3 hydrogen bonds to water, making it extremely soluble in water. So, alcohols can be classified as primary, secondary, or tertiary. So for example, this carbon is bonded to one other carbon. That's why it's called a primary alcohol. This carbon is bonded to 2 other carbons. So it's a secondary alcohol, and this one is a tertiary alcohol. So that does make a difference especially in terms of oxidation. So let's look at the chemical properties of alcohols. The first one is an intramolecular dehydration. In other words, you're forming an alkene. Here's where I'm getting my water from, either here or from here. That's how I get my water. It's, let's say, it's, what's the word I'm trying to think of? Catalyzed, I guess. It's catalyzed under acidic conditions. Because what you're trying to do, if you put another hydrogen on here, you've made now an excellent leaving group. Water can leave. You can imagine that water leaves and then you have carbocation right there. Anyway, but not that important. We don't really care about the mechanism right now. So what you need to know, if you saw this right here on an exam, would you be able to write the rest? That's what you should be thinking about. So what happens if I take an alcohol and it's under acidic conditions and I have an arrow? Well, again, you should be thinking about what small molecules can come and go from a molecule. And one important one is water. So I can take water from here. Notice that I cannot take water from the hydroxy group and the hydrogen from the same carbon, because that would leave that carbon with 2 places where it's very, very unstable. If I take it from here, that's unstable and that's unstable, but it's not the same atom having all that instability all at one time. So if I take it out from here, the double bond would go right there. So that would be that product right there. If I were to take it out from here, then the double bond would go right there. So that's that product right there. So 2 possible products. Which one is going to be prevalent? Well, Seycheff's rule states that the pore in hydrogen get poorer. It's really the opposite of Markovnikov's rule. What you're really doing, that gives it extra stability, is that the most branched product will be more stable. That's because of what happens in the transition state. So think about it. This reaction is really the reverse of reaction number 8, right? Where you're putting water into the double bond, and then you use Markovnikov's rule. And now Seyshev's rule is the exact opposite. So Markovnikov's rule was the rich get richer, and Seyshev's rule is the poor get poorer. Which sounds a lot like United States, oh, and every other country in the world. Human condition. So which one is poorer here? This carbon right here has 2 hydrogens. This carbon right here has 3. So this carbon is the poorest in terms of hydrogen, so it's going to get poorer. And that's why we get that as our major product. Okay. So this one is intramolecular. We can also have an intermolecular dehydration. And here you form an ether. So think about it. What it would look like on an exam. Here you would see this. Here you would see this. You have 2 alcohols together. So yes, I could take water from here. Won't do it. Or I could take water from here. Doesn't work good. But it doesn't matter which one. Okay, I'm just going to take water. That means I'm taking the OH. Well, let's assume I'm taking the OH off of here. That carbon wants another bond now. Then I take the hydrogen off of here. That oxygen wants another bond. And so being the generous person I am, I let them have that bond. So that's how we get this bond right here. So this is an ether. Ethers are a carbon bonded to an oxygen bonded to another carbon. Okay. Ethers are pretty inert. They're fairly stable. So once I do this dehydration and I make the ether is more likely to remain because it's more stable than these 2 alcohols together. So you will ask questions when you have them, right?
Yes.
Okay, the next one is oxidation. So oxidation is the loss of an electron, the loss of a hydrogen atom because that has an electron, or the gain of an oxygen atom. Because oxygen is the second most electronegative atom on the periodic table, that means if you're any element other than fluorine, you form a bond with oxygen, oxygen is taking your electrons away. Maybe not totally, but at least partially. So I would tell you that I want to symbolize the oxidizing agent. And 2 ways to do that. One is X, that's good for some things, and just O is good for another thing. Depends on what oxidation is going on. I like to use X because we know what X is going to do. X wants to become XH2. Okay. So here's an example. NAD is a biological oxidizing agent. It takes 2 electrons and 1 hydrogen and forms NADH, leaving 1 hydrogen off on its own. In other words, if you do this reaction, you increase the pH, right? Or you decrease the pH. And then some enzymes use NAD, some enzymes use NADP, simply a phosphate added to the NAD. It does the same thing. And flavin mononucleotide simply takes the 2 electrons and the 2 hydrogens. So these are oxidizing agents in biology. These are reducing agents in biology. So,
Do the reducing agents just have an extra H? Sorry.
do the reducing agents have what?
It looks like there's just like an H added on top then.
You mean over here?
Yeah.
Well, okay, you look at NAD, right? It has that positive charge, right? If I put one electron on it, then it's neutral. Then if I add one more H with an electron on here, that's also neutral. That's what it's gained. So it's actually gained 2 of the electrons and 1 of the hydrogens. And the other hydrogen is off into the media in the solution.
Okay, that makes sense.
Good. So what happens if you oxidize an alcohol? And again, I want you to think, what if you had this on an exam? You're staring at this, not knowing quite what to do until you realize that that's an X. And what does X want to do? Turn into XH2. Not XH, always XH2. So that means I have to take 2 hydrogens from this primary alcohol. And because we are talking about alcohol, it's the alcohol functional group that would have to be involved. So there's one of the hydrogens I'm going to take off right there. And where's the other one? Well, either this one or this one. So I make my XH2. Now I see that that oxygen needs another bond. So does that carbon. So I generously let them have that double bond. And you get an aldehyde. Okay. So in general, a primary alcohol is oxidized to an aldehyde. You can memorize that, or you can go and look at, oh, here's X. What does X want to do? It wants to do XH2. Are there 2 hydrogens that are available on the molecule? Yes. In fact, what you should be doing is a combination of those 2 mentalities. What about a secondary alcohol? I see this on an exam. X wants to do what? Turn into XH2. So I'm going to get 1 from the functional group, and here's another one I can take. So that's my XH2. Now the oxygen needs another bond, so does the carbon, so I give it to it. And here I get a ketone. So if I oxidize a secondary alcohol, I get a ketone. What about a tertiary alcohol? Okay, here's 1 hydrogen I can get. So I go to this carbon, is there any hydrogens right here? The answer is no. I cannot make XH. It is not stable. Okay? If I tried to do that, I would get these radicals formed and they're just not stable. So the whole thing just simply won't happen. So why am I not taking a hydrogen from here? What do we know about hydrocarbons? They're non-polar, the electrons are shared equally, therefore all the atoms are happy and not reactive. Okay. So you can't oxidize a tertiary alcohol. So in the lab, say you're doing an experiment trying to determine the structure of something, and you know already that it's an alcohol from infrared, IR signals or something like that. Well, is it a primary, secondary, or tertiary alcohol? Well, you would oxidize it and see what your products are or not. So here's some examples. Ethanol is oxidized using NAD in your blood where there's an alcohol dehydrogenase. So it makes XH2. and you're taking the two hydrogens away, and you end up with acetaldehyde, and that's what gives you the hangover. Methanol, you take X and turn it into XH2, same enzyme, by the way, then you get formaldehyde. Causes blindness and death. We'll see later on that primary alcohols can be oxidized to an aldehyde, and then later on also oxidize into a carboxylic acid. So you notice how I use this symbol for oxidation. That's convenient because no matter where that oxygen came from, whereas potassium permanganate or whatever, it simply goes and inserts itself in between the carbon and the hydrogen. That's how I get this. Okay. So questions so far?
For the example with NADH, why does it not become NADH2? You said X wants to become H2. Or X wants to become XH2.
We'd have to look at the structure for me to show that to you, and we will do that in another chapter quite far from now. So right now, you just have to realize that NAD takes 2 electrons and 1 proton, and it leaves the other proton out into the solution. Okay.
Okay.
So I think I showed you that. Yeah. So what does it really do? So it takes the 2 hydrogen atoms and it does what's called a dissymmetric reaction. So 2 electrons go onto the hydrogen, forming the hydride ion. And it's actually the hydride ion that NADH takes. Okay. That makes sense? So the 2 electrons are there and has a -1 charge. So when you add that to this, then you get this. And this is just left out into the solution.
Okay.
So what about naming ethers? Ethers, like alkyl halides, are not given the full status of being a functional group. So the root is the longest continuous chain, name it as an alkane, and the substituent is known as an alkoxy, such as methoxy or ethoxy. So if your big giant molecule here was named Ralph, and then you have an ethyl group as a substituent on it, it would simply be called ethoxy-Ralph. And the common names are still used for the small ethers, and you'll see this in a minute. So I'm looking at this one. The longest continuous chain is ethane. So what is the substituent? It's methoxyethane. And in the old-fashioned way, this would be methyl, and this would be ethyl. And so notice that they didn't use alphabetical order either. They used a priority system. And you can see the lowest priority was methyl, and the next priority was ethyl. And then it's this name, well, what is the functional group? Oh, it's an ether. So this one, the longest continuous chain would be 3, right? So it's propane, but on the propane at number 2 position is also a methyl group. So 2-methyl propane would be all of this. But then in addition to that, you have a methoxy on it, on carbon number 2. So 2-methoxy, 2-methyl propane. Its common name would be methyl, and then this would be tert-butyl, and then it's an ether. So sometimes it's called MTBE, and that's what they use in gasoline to replace the tetraethyl lead.
Aren't there 2 methyl groups on carbon number 2? Or how do you count? Do you count the
Oh, long-
oxygen as 1?
No. It's only carbons that get numbers. So 1, 2, 3, or 1, 2, 3. The longest continuous chain is propane. That's why I really suggest that you, if it's on a paper, you would draw a line through this to find your longest continuous chain. Then that is a substituent, and that is a substituent. So what are dioxanes? Because some people have heard of dioxanes and they, oh, dioxanes are bad. How do you make them? So if I take 1,2-ethane-diol, which is also known as ethylene glycol, and I take 2 molecules and I face them towards each other and I do 2 dehydrations, I get a cyclic compound. Okay. So this one is called 1,2,3,4,1,4-dioxane. But really they are diethers. Okay? Just a diether. I'm not going to ask you to name diethers like with these kind of nomenclature or anything, but just realize that this is simply alternative reaction to this, right? Reaction 13, excuse me. So what about the physical properties of ethers? Well, they do have carbon to oxygen bonds, which are polar, but they can't hydrogen bond with themselves because they have O's, but they don't have OHs. Okay? So the strongest attractive force would be dipolar attractions that makes them liquids, but they have low viscosity, high vapor pressure, meaning that they're volatile. They evaporate fairly equally. They evaporate fairly quickly, I should say. They can also form up to 2 hydrogen bonds with water. So let me see if I can get this to work again. Okay. So let's just take a simple ether. So here's a partial negative, here's a partial negative. The partial positive would be on the carbons, but that doesn't really be involved in anything like hydrogen bonding or anything. So if I'm looking at water, hey, come on, there we go. That partial positive negative would be attracted to a partial positive. That would be the water molecule. So here's a dipole, here's a dipole. That's not showing up, it's showing up only to me, but here's a dipole here, and there's a dipole there, right? So here's the OH of one, here's the O of the other, that's a hydrogen bond. This would attract the partial positive of another water molecule. That's another hydrogen bond. And even if I did put the partial positive on the carbon, that might attract the partial negative of a water molecule. And that would be a dipole to dipole attraction, right? But notice when we're talking about alcohols and attractive forces, we're not even talking about London's forces because they're so weak, even though they exist. And what did we say about a dipole attraction versus a hydrogen bond? hydrogen bonds are stronger. So what we're always talking about is what is the strongest attractive force between two things. Okay. The other thing is they're not very chemically reactive, so they make excellent polar solvents. The problem is that they're very flammable. Because they vaporize, they're dangerous. It's like people don't realize how dangerous gasoline is. Gasoline is dangerous because it evaporates quite readily, goes into the vapor phase, mixing intimately with oxygen in the air, making it an extremely explosive situation. On the other hand, diesel fuel is not very volatile because the particles are heavier. So that's why they use diesel fuel in a lot of like boats and trucks and stuff like that that might get quite hot engines. But you can take a container full of diesel fuel, throw a match on it, the match just goes out. Just goes under the liquid and goes out where there's no oxygen. And so, yes, ethyl ether has been used as an anesthetic, but again, it's very flammable and very dangerous. So let's look at the chemical properties of ethers. So the first one is simply hydrolysis. If you saw this reaction on a test, you're like, oh, water has to go in there somewhere. It's not going to go in between two carbons. Remember, all this is inert. It's the functional group. So I'm simply doing the reverse of reaction 13. So the hydrogen would go on here, making this a positive charge, causing this negative charge to attack it. Then the leaving group would be one alcohol, and what you have left over is the other alcohol. Okay. So ethers can be hydrolyzed into alcohols. Alcohols can be dehydrated into ethers. And then this one is not important in terms of biology or even organic chemistry necessarily. But I put it in here because it's a warning. Here's an ether. Look what happens if I take an oxygen and put it somewhere. Is it going to go in between two carbons? No, because the difference electronegativity is 0, not reactive. What about in between the carbon and the oxygen? Yes, it can do that. And when you do that, you get a peroxide. And what do you know about peroxides? They're extremely reactive. Also, you can oxidize it a different way. If I were to take two hydrogens off of here, well, I did it down here, to make XH2, then that carbon needs another bond, that carbon needs another bond, and look what happens. The cyclic ring can form, and that is an epoxide. And why are epoxides volatile and reactive? The bond angles here are 60 degrees when they want to be 109.5. Why would this reaction even happen? Because if this is reactive enough, it will make this happen. So especially in the laboratories, ethyl ether has exploded and people picked it up and hasn't been taken care of correctly. And people have been injured from exploding ethyl ether. So it's not the ether itself that explodes, it's the epoxides or peroxides that explode. And what we said about the ethers is they're very volatile. So it can be quite dangerous. When we store epoxides in the lab, we have to test them, not epoxides. When we store ethers in the lab, we have to test them every year for either peroxides or epoxides. What about phenols? So this you have to remember now because we've covered alcohol. So that's phenol. Here on the 2 position is a methyl group, so methyl phenol. We could say the 2 position, or we could say this is ortho. So these 2 carbon atoms right here are ortho. These 2 carbon atoms are meta. That 1 carbon atom there is para. And phenols can form up to 3 hydrogen bonds with themselves and with water. So I guess I could, since I'm getting good at this now. So here would be a partial positive. This would be a partial negative, but so is this one down here. Okay. So that partial positive would attract the partial negative of another phenol molecule. That would be the electron clouds on the oxygen, right? Okay. Also, this partial negative would attract the partial positive of another phenol. That would be the hydrogen. Okay. And similar thing down here. Okay. Oops. So I'm looking at the one in blue. Here's the OH. All I need in the other one was an F, an O, or an H, and here's the O. Okay. Then I'm looking at the oxygen, the partial negative is attracting the partial positive. So here's the OH of one. All it needs in the other one is an F, an O, or an N. There's the O, hydrogen bond. Similar thing with this one, right? Then I could replace these with water. What would it look different? Not much. I'm simply taking off this and I'm putting the hydrogen. Right? So, what about the chemical properties of phenols? Okay, well, one interesting thing is that they're weak acids. It's like, what? Why would that be an acid? That's an alcohol. But yeah, they are. So notice that I have a 2-directional arrow here because water is a weak base. So it's not going to be a strong reaction, a weak acid and a weak base. I'm only going to get an equilibrium, so I'll make some of this and some of this, but that affects the pH, so it's an acid. If I put phenol in with a strong base, I will make it go all the way to completion. Okay. And notice that this is called a phenoxide ion. Well, here's the reason why phenol is a weak acid. It's not necessarily because it wants to get rid of that hydrogen so badly. It's because what happens when it does get rid of that hydrogen? So here is the phenoxide ion, right? What we drew up here. But look what it can do. So we don't have reaction mechanisms here. Can't draw on that. Anyway, I got one more thing I got to figure out with this iPad. And it's very difficult for me to show you without being able to draw arrows here, but we can make resonance structures. I take a non-binding electron pair from this oxygen and I swing it and make a double bond right here between the oxygen and that carbon. That negative charge swinging this way pushes this negative charge away. So those two pi electrons end up as the negative charge on this atom in the ortho position. Then I can take this and put it into a double bond here, and these electrons chase up on top of that one. Now it's in the para position. Then I can take this and put the double bond there, that chases up on there, and you see I have it on the ortho position again. So in other words, the most predominant feature on the phenoxide ion is that negative charge. If I can find a way to decrease the magnitude of that negative charge, I will make that molecule more stable. And here, I've spread it out over 1, 2, 3, 4 different atoms. So that's what we've done. We've made the magnitude of that negative charge much less, so it's much more stable than it would be if you couldn't do resonance structures. So phenols are used as antiseptics. They're polar enough to dissolve in water. They're non-polar enough to dissolve through the cell membranes of microbes. And once inside there, they can act as weak acids to destroy cellular components. Phenol was also one time called carbolic acid, and it was used in the 1800s by Dr. Lister as a surgical antiseptic and pain reliever. It's still used in chloroseptic. So yeah, Listerine came from Dr. Lister. So I did an experiment one time on myself. When I was a graduate student, we were sequencing proteins, and you would commonly put phenol into our containers to prevent the oxidation of certain amino acid components. So anyway, one time I picked up a sliver of it off the table and I said, well, what happened if I just leave it there on my fingers? So I left it on there for about half an hour. It's like, oh, it starts to feel a little bit funny. Anyway, so I washed it off, I went home, took a shower, and then I noticed that my finger where it had touched had turned all white. The skin was all white. And then a couple of days later, that pieces of skin just fell off, which means it took all the collagen and everything in my skin and simply depolymerized it. So yeah, bacteria and viruses don't like that. And then phenol can also be oxidized. So here's something that I saw as an undergraduate, and I'm like, what the heck is this? How does this happen? And they didn't give you a complete reaction. They didn't explain anything, and I was just perplexed by that until finally I sat down and, as I was writing this textbook, and said, I got to know stuff, why things happen. And anyway, here's a chemical reaction that does happen. So if you know a lot about aromatic substitution, then you'll see that the hydroxy group promotes aromatic substitution in the ortho and para positions, and this is the para position. So when you dissolve it in water, there's so much water that it forces the equilibrium to go that way. And then the hydroquinone, which this is now called, can be oxidized. So you get the semiquinone, and here's two resonance structures, right? But unfortunately, I stole this because I just not able to draw all the things. I'm not how do you say, a graphic artist. But the non-binding electron pairs right there could be swung into a double bond right here, pushing this one up here and then that one over there, and you end up getting what's called a semiquinone. Notice that that's a single step oxidation. This is a rare case where you can actually form XH instead of going directly to XH2. But if you just leave it long enough, it simply goes all the way and you get what's called a quinone. So what is a quinone? It's actually a diketone. So here's a ketone and here's a ketone. So a semiquinone is a ketone. Okay. And so phenols that can undergo these type of oxidation reactions can be used as antioxidants. They're designed to use this up to protect something else. So this is an oxidant, right? So an antioxidant is to protect something from an oxidant. So if you look at many of your foods, they'll have BHA and BHT, one or the other, or maybe even both. And those are antioxidants. So here's a bunch of them. Let's see. Here's BHA, here's BHT, here's some other ones over here. Here's what BHT does. So BHT is a phenol, but notice that it forms these conjugates. So you get two of them together, they get oxidized, and look at all this stuff. It's completely conjugated over here. So it can absorb actually quite a few molecules of oxygen. So why would you put antioxidants in your food? Because mostly to protect unsaturated fatty acids, the oils that are in your food. So oxygen can oxidize those into aldehydes and carboxylic acids, and it ruins the flavor. It gives the rancid smell oftentimes. It's from chemical reactions, not only from microbial activity. And so what you're trying to do is you put BHA or something like that in there, and as soon as an oxygen molecule tries to attack the unsaturated fatty acids in your food, it goes, no, I'm more reactive, take me first. So vitamin C is a natural water-soluble antioxidant, and vitamin E is a lipid-soluble antioxidant. So why do humans require vitamin C? Okay, well, here's how you synthesize vitamin C. You synthesize it from glucose. So glucose gets turned into this glucuronic acid, then a different glucuronic acid. And what is NADH right there? It's like an XH2. It's being reduced, right? So you're reducing it over here, you're dehydrating over here as you make the cyclic form. And then some, how do you say this? Most animals have an enzyme that goes the next step and you form vitamin C. Humans, that gene has been mutated. We can't make it. So when this phenomenon started to happen in the human population, it didn't really have much of an effect on the survival, because humans were eating enough fruit and everything else that they were getting vitamin C from the fruit. So to take away the ability to make vitamin C, not that big of an issue. That's why it's persistent. So in not all animals, vitamin C is not even a vitamin because they can synthesize it. Humans and some of the apes, we've lost that ability. So how does ascorbic acid or vitamin C, how does it act as an antioxidant? So it gets in there and it takes, what's the word? Yeah. It takes, well, it destroys the oxidizing agent. It gets oxidized instead. So notice as you go this way, you're getting more and more oxidized. So if you go this way, you're taking away an electron, right? And you put in water and you just hydrolyze that. But you see there's more, this is more oxidized over here than this is over here. Here's a secondary alcohol. I got oxidized to a ketone. Essentially a secondary alcohol got oxidized to another ketone. What about thiols? So you name them similar to the alcohols, but you replace the word all with thiol. And unlike alcohols, we keep the E. So this would be methane thiol, ethane thiol, propane thiol, butane thiol. But notice in these two cases, I have to say where the thiol group is, because it could be carbon number 1, carbon number 2, right? That'd be 2 and that'd be carbon 1 again. So these right here are extremely potent smelling. So they put very small amounts of them into natural gas so that the natural gas can actually be detected. Otherwise, natural gas has no smell, and that would be quite dangerous. And so here's one propane thiol. This is found in onions. Do you guys like onion breath? I actually like onion breath, and I don't know why everybody's against onion breath. You put onions on your food because you like the taste of it, and half of the taste is olfactory, it's your smell. So if you don't like the smell of onions, you wouldn't be putting it on your food. But this is one of the components found in skunks. Anybody like skunk breath? And what's the difference? This one CH2, one methylene group, and you turn an onion into a skunk. So here's a couple more that are found in skunks. So notice that this has a thiol and it's also an alkene. So how do you handle naming a compound that has more than one functional group? Well, it becomes a little bit complex. That's why I'm not going to ask you to do it. Also found in skunks. And the common names were simply called a mercaptan. So this would be called methyl and a mercaptan. Instead of methyl alcohol, be methyl mercaptan. And thiols are fairly nonpolar. If you look at the difference in electronegativity, it's really like a carbon in an oxygen. I mean, carbon in a hydrogen, I should say. So they're not capable of hydrogen bonding. They're not capable of dipolar attractions. So thiols are volatile liquids, and they go into the vapor phase, and when they do, they stink. They're fairly soluble in water due to weak attractions and low molar masses. Okay. So sulfur is considered to be polarizable So the London forces that it does is capable of can be fairly strong. So what do I mean by polarizable? So if you compare oxygen with sulfur, the valence shell electrons in oxygen are in shell number 2, but in sulfur they're in shell number 3. So they're farther away from the nucleus. They're more easily moved around and deformed. In other words, polarizable during a collision, which would be describing a London's type of force. So what are the chemical properties of thiols? Well, they can do oxidation and reduction, and these are readily reversible, even under biological conditions. That's why I just gave one reaction. So if you saw this on a test, what you would be thinking is, oh, X wants to turn into XH2. So I take a hydrogen from here to make my XH2. Now sulfur needs another bond, so does that sulfur, so you let them have it. And you end up with a disulfide. If I saw this on the exam, what does XH2 want to do? It wants to turn into X. So it's going to give us hydrogen atoms to something. What would it be? Something to do with the functional group, right? So the disulfide can be converted back into individual thiols under most conditions. So disulfide bonds are important in protein structure. So here's two pieces of a protein that are separate. They can be oxidized by an enzyme. So X wants to go into XH2. And now you just join these pieces of protein together with a covalent bond. So disulfides are usually named with a common nomenclature based upon polysulfides. So this would be methyl disulfide or dimethyl disulfide. Here's 4, 5, so this would be pentyl, this would be hexyl disulfide. So you just use the word disulfide. You guys ever see a skunk? So my sister, just younger than me, went to the mainland for college. She never came back. Same with all my sisters, all my cousins, they all ended up on the mainland. Even my youngest son is on the mainland. But anyway, my one sister, Cindy, studied forestry and all this kind of stuff, and she became a backcountry ranger for the National Park Service. And so I remember visiting her and her kids one time, and we're walking around the forest, and oh my God, is that a skunk? It's like a mongoose with a racing stripe. And that skunk was just cruising around the forest like it wasn't afraid of anything. I'm asking my sister, aren't there bears and stuff here? And they go, yeah, but they don't bother the skunks. So the skunk is king of the forest. So do skunks hate their own smell? If a skunk gets sprayed in the face by another skunk, it reacts just like a dog. Anyway, it's a very, very bad smell. And one of my favorite cartoons, look at that dog. He's like, if you think I'm gonna mess with this guy, I'll just let him eat what he wants. He won't eat everything. I'll live to fight another day. So skunk odor can now be destroyed. see. They found these natural compounds that made by certain molds, and what it does is it simply takes, where to go? This molecule takes the thiol and basically does an SN2 type reaction with it, and you end up with this product over here that doesn't have a smell. So in other words, the thiol over here ends up onto this, how do you say, anti-skunk molecule. So it makes one think about immature stuff. So my wife and I were cleaning out one of the offices at her school. She's a vice principal. And the office was now going to be used in case a kid comes down with COVID-19 or suspected of that. They're going to have a room to put the kid in isolation. And it used to be a vice principal's office. And so I found these little packets. They were called stink bombs. And I immediately thought of my one friend. So I saved them and gave them to him. I had 2 of them. So he used one on his wife. And the wife was so impressed that she took it to work and used it on her coworkers. And I'm talking about people who are in their 60s, you know what I mean? Doing these kind of things. But the first stink bomb was probably made in Germany using thioacetone. And what were they using it for? Chemical warfare. So the United States Defense Department contracted in 1998 to produce a stink bomb for warfare. There's even a book about it. Yeah. Anyway. So I guess we went through the entire chapter.
Can
Anybody?
you review the naming the disulfides again? I'm confused why we don't put like numbers, like 1-methyl or 1,2-methyl.
Okay. Where'd it go? Files. Oh, here. So notice that we're naming it just like how we did the common names for ethers. Instead of having 2 sulfurs right there, if I had an oxygen right there, it would simply be called dimethyl ether. So this would be called pentyl hexyl ether. So it's just using that style of nomenclature. We also have sulfides, which I didn't talk about. So that was a single sulfur in here. It'd be called dimethyl sulfide, pentohexyl sulfide. So it's just a different style. And what people don't really understand about IUPAC nomenclature, if you actually went and looked up all the rules for naming by IUPAC, you would be able to spend your whole life, your whole chemical career just trying to name things. It's just extremely complicated. Not only that, they change things every so often, and so you have to deal with those changes. So for certain things like ethers and disulfides, we just go with the old-fashioned simple way because most of them are going to be very small and simple anyway.
Okay, so if there's a H on the sulfur, it's a thiol, and then if there's no H, it's a sulfide.
Right.
Okay.
So hold on a second. So say you had this, right? That's a thiol. Oops, wait, I did want that. Okay, what's the deal here? Okay, this is a disulfide, and, which we didn't cover here, this is simply a sulfide, right? So most of the time when we name these things, we simply call this by its functional group, which is a disulfide. We name this as a sulfide. That's the name of the functional group. So this would be dimethyl sulfide, dimethyl disulfide. But this, thiols, we do a little bit differently. We could say methyl mercaptan, mercaptan, but we don't normally use mercaptan. So with thiols, we usually use, the regular name, right? So methane thiol, and we don't need to put the number 1 there because there's no other choice. Does that make sense?
Yes, thank you.
Trying to see where I put the syllabus. I can't find the syllabus, so I'm gonna go pull it up on the Lima site. Okay, so here's the syllabus. So we're in, oops, where are we? We're still in week 1, right? So we're here. So we're doing fine for the schedule. So maybe we won't, let's see, we started at 1:30. Maybe we won't go into stereochemistry today. That way we'll have separate videos for each one. So, but tomorrow we'll start stereochemistry. And I would suggest that if you have any questions about chapters, up to the previous chapters, that you ask them tomorrow. Tomorrow being Friday, because I think we will finish chapter 24, and then our exam somehow is coming up pretty soon. I hate exams. How about you guys? You like exams?
No.
Oh,
Yeah, I hate exams. So anyway, I think that's what we'll do. We'll stop the lecture today, and tomorrow, which is Friday, we'll do stereochemistry, and then, yeah. I really cannot stop the lectures. We have to just keep going, and pushing, because otherwise, if we mess around over here, we're going to just get ourselves behind, and it's just not worth it. So if we look at I can find my screen share button, should be put somewhere else. My windows are all on top of each other. So let's see, that's 18, that's oxidation. 19, disulfide formation. So for exam 1, you have 19 chemical reactions to know about. Okay? Reactions 1 through 19. So as you formulate questions, you might want to think about that. And what would the exam questions look like? I tried to point that out today. You're going to have naming. You're going to have physical properties where you may be asked to draw a hydrogen bond. And then the only other thing is chemical properties. So on the chemical properties, what would you see? You would see this. That would be the exam problem. And what do you have to do? Show me the other part, right? There's nothing tricky. It's simply that. There's no reaction mechanisms, nothing like that. Does that make sense to you? Does that help you think about what kind of questions to ask?
Yeah, so is stereochemistry not going to be on exam 1 then?
Say again?
So is stereochemistry not going to be on exam
Oh,
1
it
then?
is. It is, but there's no chemical reactions in it.
Oh, okay.
Yeah.
Is it going to be handwritten, or are we going to be using a program to type it all out?
I think I might just send it to you as a PDF and then maybe have you send it back. I'm not sure. So I'm on this system-wide committee. We just met just before this class, and we don't even know what's going to happen to testing centers. Right now, all the testing centers are just down. They're not even in functionality. And so at the Manoa campus, we're trying to put together a huge testing center, but they meet on Monday. That committee meets on Monday. So I'm not sure exactly what they're going to do. So we're just messed up right now. We have no way to test. And first summer session, I caught students cheating. They were all cheating. But there was 2 that were Skyping to each other, and their exams were started and finished at the same time all the time. They were Skyping. It's just a real mess. And then when you write an exam and you put it out there in a digital form, everybody has it from now on. That means that every time you teach that, you got to write a new test. It's very, yeah, it's a mess right now. So I'm not sure how we're going to do it, to tell you the truth. But we'll find a way. And I'll go look up those study guides. They're not pretty, but I'll find one. Let me write that down right now. And get it up there. So any other questions? Okay, well, we'll finish here and I'll get this up on the YouTube site as soon as I can. So you guys have a great day.
Thank you. You
Thank
too.
you.
Thank you.
Take care.
You too. Thanks.
See ya.